Okay, sorry about that, guys. Excuse me, I changed the problem from what I normally do because I wanted to make a point about this later, and I just, I just completely messed up here, and I used point 0.4 instead of point 0.6 for this. But I'm back on course now, and I tried pausing it, but it quit on me, and that's fine. All right, so let's talk through this. I'm dealing with my first field created by charge number 1, and it is 9 times 10 to the ninth times the charge that is creating the field all over the distance away from my test charge, 0.4 plus 0.2, so that the size of the electric field around this is 9.72 times 10 to the ninth newtons per coulombs, and it's pointing in this direction. You don't need to put this here because it'll all turn out when you're doing the net field. And then I do the same thing for this charge number 2. What field does charge number 2 create? And 9 times 10 to the ninth times 1, which is the charge on my Q, times 0.2, which is the distance from this charge to my test charge. I do the math on that, and I find that it is 2.25 times 10 to the 11 newtons per coulomb toward it, because it is moving in this direction. And when I set this all up, it's going to be sigma E sub x is just my two fields cosine theta, but in this case it's all in a straight line, so it's going to be cosine of 0. So it's 9.72 times 10 to the ninth cosine of 0 minus 2.25 times 10 to the 11th cosine of 0. This is negative because my test charge is moving toward the negative, positive towards the negative, so it's moving in the negative x direction. All right, when I do all the math with this, I find that my x component is negative 2.15 times 10 to the 11th when I combine these two together. There is no x sub y because everything is happening as no e sub y because nothing is happening on the y-axis. So all of my field is my x line. So it's a negative 2.15, or now it's just going to be 2.15 times 10 to the 11th newtons per coulomb toward the negative, or toward all of the charges, in the left, towards the west, toward the charges. You can describe it any way you want as long as you are giving me a direction of the field. And one more, and we'll talk through this one. Now I have three charges. I have a 10 coulomb charge, a negative 5 coulomb charge, and another negative 5 coulomb charge, and my test charge, which is positive. Don't care the magnitude, but I do need to know the distances. It's 2 meters, 2.5 meters, and 3 meters. It has to be meters, even though I have not been labeling it as meters. It has to be meters because as soon as I've got newtons in there, I know that everything has to be in meters. And my 9 times 10 to the ninth is based on meters. And the angles are going to be, this is at 70 degrees from the x-axis, this is 75 degrees from the x-axis, and this is 15 degrees from the x-axis. I have three charges, therefore I'm going to have three fields. So my first field is 9 times 10 to the ninth times the charge itself divided by the square of the distance, and I end up getting this measurement. This same thing, I don't put the negative in, that's taken care of down here, divided by 2.5 because that's the distance from there. And this is my field caused by just this charge. And this is the field caused by the last charge, go from left to right. That's the magnitude of it. All right, so I've got my three fields and I need to add them up. And the only way I can add a vector is by adding it by the component method. So I do my sigma E sub x, which is all three of my fields cosine theta. And this one's positive because, give me a second here. This one is actually negative, yes. I should have drawn this one out and I apologize for that. It actually, my test charge is going to look like this. And they're all positive, by the way. But I should have actually written it out. in terms of what it looks like. So my positive charge, because of the presence of that, my positive charge is going to be pushed away at 70 degrees. So this would be 1. My positive charge is going to be pulled towards at 75 degrees. So this would be 2. And it's going to be pulled towards this negative. So this would be 3. Okay, so you notice that all 3 of these are in the positive x direction. So I'm adding all of them up. And it's cosine 70, cosine 75, cosine 15. And this is what I get for my result for sigma e sub x. Sigma e sub y, same thing, only now I'm doing sine, and I have to be careful of my signs, S-I-G-N-S. This one is below the x-axis, and since it's below the x-axis, it's going to be negative. So I have a negative 2.25 times 10 to the negative 10 sine of 70. The other 2 are positive, so I just add them up. And I end up with a negative 1.29 times, where am I at here? 1.29 times 10 to the 10th newtons per coulomb. To find the result of those 2, or the resultant, I use my Pythagorean theorem formula. 1.93 times 10 to the 10th newtons per coulomb. Theta is equal to the inverse tangent of of this over this, and you know what? I never did find theta. Let me find it for you here real quick. So it's 1.29 times 10 to the 10th divided by 1.44 times 10 to the 10th is equal to, and then I take the inverse tangent of that, and I get 41.9 degrees. I'm not promising that's right. Double check my work on that. 41.9 degrees, and because this was positive and this was negative, that has to be in quadrant 4. The positive x and the negative y. Positive x, negative y, quadrant 4. All right, so that's how you find electric fields. I want to spend just a couple of minutes talking to you about what it actually looks like when you're drawing the lines of force around an electric field. And on the back of this page, I'd like you to write what lines of force actually are. Lines of force, electric fields can be represented by drawing what are called lines of force, which are 1, lines that show strength and direction of a field. And under that, I'm reading ahead here. Under that, letter A, the closer together they are, the stronger the field is. If the lines are close together, the field is strong. If the lines are far apart, the field is weaker. And it always points, you can kind of see by my drawings here, it always points away from the what and toward the what. It always points away from the positive and it points toward the negative. So please write that down. Always points away from the positive toward the negative. So this is how I would draw the lines of force around just a positive charge. This is how I would draw the lines of force around just a negative charge. And if I have a positive and a negative charge, like I did for my first one, if I have a positive and a negative charge, I would draw the lines of force like this. The lines of force are always going to be going in towards the negative and away from the positive. And what's happening here is they're being deflected a little bit because there's an electric field over here that is pulling at it. So it's going to it wants to go away, but it's being pulled in. It wants to go away, but it's being pulled in. And your field here actually is the tangent. If I put a positive charge right here, it would be the tangent to this line. And because it's positive, it's not going to be pointed towards that. It's going to be pointed toward my negative. And then this is what it would look like if I have this is what it would look like if I had 2 positives together. They would be deflecting each other because they're certainly not going to want to draw lines of force together. That would be like if you had 2 north poles together, it would do this same configuration. They want to move away from each other. So you're going to have this gap in here that does not have any lines of force in it at all. It's kind of a no man's land in there. And again, the closer they are together, the stronger the field. So I have a really strong field right here. I have less of a strong field here. The farther away I go, the farther away the lines of force are going to get. There was something else that I wanted to show you that's kind of a unique consequence of all of this. And let's say, for example, when I did that one charge and I had a positive test charge here and I had a negative test charge here, a positive fundamental charge or original charge there and a negative original charge here, when I put my test charge here and I were to ask you what direction would it be pulled, because there is going to be lines of force in there that are causing it to be pulled, in what direction is it going to be pulled? And you would guess, and probably correctly, it's going to be pulled in this direction. So let me say again that this one is 3 coulombs and this is 1 coulomb. Because this is so close, you're going to assume that it is going to go in this direction, even though the positive wants to push it away and it is stronger. It's the proximity of it that makes you think that. But what if I put it all the way out here? Now all of a sudden, this distance between them is really virtually meaningless, because now it's this far away from both of them. So at this point, what's going to end up having the stronger influence is going to be my stronger charge, because this little bit of closeness between them becomes less and less significant as the charge gets farther and farther away. So what's going to happen is, when it's this far away, it's going to be pushed in this direction. So it starts out going towards the negative, and over here it's going to go away from the negative because of my positive charge. Interestingly enough then, at somewhere in between here and here, and you'd have to quantify that, and I'm not going to go into showing you how to do that, but you can quantify this to say that somewhere in between, if it starts out going this way and ends up going this way, at some point there is in between there where E is equal to 0. So the electric fields cancel themselves out as it's switching over from being attracted to the negative to being repulsed by the positive. Kind of an interesting effect that happens when you have fields working against each other, as in that case. All right, your homework for tonight, excuse me, I will post on PowerSchool for you. And if you have any trouble with it, let me know. But it's pretty, it's going to be pretty straightforward. It's a lot like, sorry about that. It's a lot like what you have been doing with your F. Now, in fact, you get to take one of the charges out entirely. But this is a little bit more difficult because it's more conceptual than it is the other stuff. So what I'm going to have you do is 32, 33, 34, and 35. Okay, there's going to be 4 of them for you to do, 32, 33, 34, and 35. And let me make sure that that is 32. No, I'm sorry, it's, you know what, I'm going to have to tell you what that is. I'll actually post it. It's either 31 or 32, but I will post that for you on PowerSchool and let you know for sure what it is. Sorry, these videos have been a little bit disjointed. This is the last one for the chapter. The physics students that are face-to-face are going to be finishing this up tomorrow. And we're going to have to finish lines of force and the rest of that on Tuesday because their class time is very shortened. And then they're going to take the test on Thursday. So be thinking about when you want to come in to take the test. We'll be starting the new chapter on Thursday and continuing from there. So I would say sooner is better than later because this new chapter is very, very similar to this, but enough different that you could easily get confused one with the other. So I would try to get this chapter test done as soon as you can. Let me know what you need.